So I hope you remember what I have said before in the last 5 minutes. I introduce MBT, what it is. I talk about the learning objectives, and I integrate MBT, that means pre-treatment before landfill, in the waste hierarchy you have and we have also in Europe. Then I come to the next slide, and from now on I will start again. What are the targets or the objectives of treatment before landfill? And you see some points, and I will highlight it in my presentation. Minimizing of volume and mass, inactivating of biological processes, mainly the reduction of methane emission, immobilization of contaminants because of reduce of leachate emission, recyclables, so take out some recyclables like metals and other components, and maybe to produce fuels from waste, RDF, that means refused derived fuel. But the overall objective of MBT, of treatment before landfill, is climate protection. The most important factor, and you will see at the end of this little presentation, I think it's around 20 slides, why this is so important. What is the situation in Germany? So 75% of all these treatments technologies are thermal technologies. It means incineration plants. And 25 are MBTs. So we start with incineration in the 50s of last century, and with MBT more or less in the beginning of this new area in the, I think we start in the year 2000. But I will highlight today only MBT because this is a part of the biotechnologies we focused on in this little lecture. So, but the main point at the moment is what kind of limiting values we have for the material which we are allowed to dispose on landfill. And we have a special law in Germany we created in the year 2001. And we have different laws and requirements from incineration residues, that means slag, and MBT materials. I will focus only today on MBT material. We have a reduction of total organic carbon in the solid. That means we want to reduce the organic matter which could be degraded on an anaerobic way, so the potential for methane gas production. Second point, we have a limiting value for the wastewater area. This is the total organic carbon in the eluate. So you want to reduce the organic components in the leachate. Then we have two other parts of limiting values. These values describe or limit the biological activity of the raw material when you dispose it. And at the end, there is a limiting value only for MBT. This is the upper caloric value. I will explain them a little bit more in detail. So, the first parameters are emission parameters. That means AT4, that means respiration rate, called how many milligrams of oxygen you need in the material you want to dispose. Sorry, I missed here. You have to give in here oxygen. That means O. Alternative, we have another limiting value. That means the gas formation rate during 22 days. That means 20 liter per kilogram dry matter. You have to know an fresh waste has an amount of around 200. So the requirement is to reduce around the activity by around 90%. So both parameters you can use alternative. AT4, that means this respiration rate in 4 days, and gas formation rate in 21 days. Around the target is reduce the biological activities by around 90%. And the same we have in the area of wastewater and groundwater protection, also a limitation of organic components. So this is one part of the limiting values. And the second part of limiting values, this is very special in Germany. Maybe, I don't think that this will come in Brazil. So we have the upper caloric value, or you can use alternatives, the TOC, total organic carbon in the solid, by 18%. What is the target behind these limiting values? The target is that they don't want that you dispose high caloric components, because it said these are raw materials, you have to produce energy from it. That means smaller 6,000 upper caloric value means more or less no plastic, no paper, and a net. So these are emission limiting values, and these are recycling enhancing limiting values. The next point, what are the critical components for landfills according to the gas production? And you remember, when you have waste, you dispose on landfill. After a short time, you don't have any oxygen in the landfill's material, in the landfill body. And so the degradation, the kind of degradation change from aerobic, that means the degradation process by using oxygen, and to anaerobic degradation, this is a degradation process without oxygen. And this is the main problem, because this anaerobic degradation process, as a product, we have carbon dioxide and, I hope you remember, and methane. And again, we talked in our first lecture about methane. Methane has a very high global warming potential. You remember what this is? I hope. There are different kind of numbers. So you have 25 or you have 28. I know some, they are 30. That means the warming potential is by the factor of around 25 higher than carbon dioxide. This is the definition of global warming potential. And you remember, for example, laughing gas. Remember the number? It's around 300 or 298. And this high global warming potential of methane, this is the biggest problem we have by landfilling of untreated waste. So you remember the technologies of composting, the technologies of anaerobic digestion, more or less these technologies are all of you, if you use it for the production of compost, or if you use it for the pre-treatment before landfill, the technology more or less is the same. So I don't want to discuss it in detail. But the main point is, for example, at first you shred the waste, you screen the waste, and in Germany you have the material bigger 100 millimeters. There you have paper, textiles, plastic. And the other components, you have a high concentration of organic matters. It means biological, degradable components. And you can screen it again. It's typical in Germany, 30 to 40 millimeters. So you have the remaining plastic and wood you take out to produce high caloric components. That means you produce a fuel. And At the end, you have a stabilized organic matter smaller than 40 millimeters. This is, again, a typical technology we use in Germany. I think in Brazil there are other ideas. For example, I know some MPT technologies, they integrate a sorting step, a manual sorting step or a fully automatically sorting step, so that you can take out plastics, that you can take out cardboard and an end. So this depends on the targets you have in your community and to the targets to your MPT treatment technologies. So on one hand, again, you can take out recyclables, or you can take out the recyclables as a fuel, as a raw material for the production of a fuel. So, but we focused at the moment in the biological stabilized material for the landfill. And again, you have a treatment process of composting or a combination at first anaerobic digestion and the post-composting process to stabilize the organic material so that you can reduce all the degradable organic components. So let's start again with the target we talked before, mass reduction and volume reduction. So we see the MPT 100% raw material, and without sorting out recyclables, you have a reduction around 40%. That means up to remaining 60% of components for the landfill. And this difference, the background for this difference is the degradation of organic matter and more or less a little bit of drying step. But if you integrate a recycling step by sorting out recyclables or taking out RDF components, then you have more or less a mass reduction by around 70%. And when you compare this mass reduction rate is more or less the same like incineration. So incineration also has as a remaining amount of slag, it's around 30%. But you have to integrate again, take out recyclables or take out combustible components. So at the end, this is a combination of mechanical biological technologies with incineration technologies. This is typical for Germany, and I think on the long-term view, you will have it also in Brazil. So the second point, the second requirement was reduce the volume requirement, the volume you need for landfilling. And in this case, it's very important. On one hand, you have the mass reduction, but as a second parameter, you need the installation density. That means, what is the density of the material you dispose on landfill? So if you have a raw material without any treatment, you have only 700 kilograms per cubic meter. And when you install it with the caterpillar. If you take a compactor, you can achieve much more higher densities, around 0.9 up to 1. But if you combine, for example, compactors with MPT material and taking out the plastic components and so on, then you have an installation density around 1.3 up to 1.6. And when you combine these two steps, these two parameters, mass reduction and lifting up the densities, at the end you see this as a result. Requirement of landfill volume per 1 ton of waste. Untreated waste 1.1, MPT by 40% mass reduction, 0.46, and with removal of recyclables and combustibles 0.23. That means factor 4 to factor 5. And this is a very important part for the target of MBT, or in general in waste treatment before landfill. So this is the information about mass and volume reduction. Now we look for the biological stabilization. And here on this slide you see the GB21. You remember the gas formation potential, or the gas formation in the fresh material, and the development during the aerobic treatment. Here you see the aerobic treatment time. So you achieve, for example, the limiting value of 20 liters per kilogram dry matter. You achieve this number after 8 to 13 weeks. For Brazil, it's a question, is it necessary to have this very strong limiting value by 20, or maybe it's 40 or 60. Here you see what kind of remaining gas potential you have. And Christiane and me, we have worked for your environmental ministry, and we gave some recommendation for this limiting value for Brazil. And we said maybe it could be totally okay to say 40 or 60 when you add later on a landfill a so-called methane oxidation layer. I will explain a little bit later. Because MBT with this methane oxidation layer at the end, in the result, has the same result. So maybe it could be that it could be very helpful, and when we take other limiting values, a little bit higher limiting values. But I will explain a little bit later. So again, untreated waste has around 200 liters of biogas per 1 kilogram waste. MBT material has at the end a reduction around 80%. And we will talk later on this methane oxidation layer. But when you see this number, 200 liters per kilogram waste, or per 200 liters for 1 ton, when you transfer it to the global warming potential of 25 or 28, then you have per 1 ton on landfill an amount of methane gas, of CB equivalent gas, then you are around 1 ton 700. So 1 ton untreated waste emitted 1 ton 1.7 or 1 ton 700 kilograms of carbon dioxide equivalent. This is the problem and the biggest requirement. We have to reduce this extremely high amount. And remember, when I explained it to you, in Brazil, the total amount of greenhouse gases from waste management is around up to 10%. It's only one area of emission. So the waste management is one of the big 6 sectors for greenhouse gas emission. So this is the background why we have to reduce the greenhouse gas emission by landfill. You can do it partly by recycling, but at the end, the most important thing is the pre-treatment before landfill by incineration or by biological treatment. So what can we also do with this components we stabilized in the biological treatment, we can produce a special filter material, a special filter layer. Because when we screen it by 30 to 40 millimeters, the fine grain is more or less a compost. And this compost you can use as a filter material. For example, you have in this area your landfill. This landfill body produced methane. This methane you bring into a gas diffusion layer, and this gas will integrate in the filter layer. This filter layer is around 120 centimeters, but in these filter layers we have, by the way of diffusion, oxygen. And in this process, in the combination of methane in combination with oxygen, we have the oxidation process. So the methane will be oxidized. And the methane will be oxidized more or less by up to 100%, but only when the amount of methane is low. So you can't use this oxidation layer. You can't use it for raw material or for fresh landfill. In this case, the methane oxidation potential, or the methane oxidation, the methane emission amount is too high. So the filter can't reduce around 100%. So the filter can reduce up to 20%, up to maybe 25%. So a very simple technology you can use in the combination of MBT and the produced output using as a methane oxidation filter. And again, when we have the beginning of 200 liters and we have around 80% reduction by MBT, and again a reduction up to 4, so we have a reduction more than 90% by the combination of MBT and the filter material. So up to 90%. What is at the end the main point? The main point is that we don't have greenhouse gas emission from landfills, only in a very few amount. But at the end, what is very important, the period of aftercare of untreated waste, of waste is much more shorter. So we discussed in Germany about 30 years, and now we have some landfills. We have to look for the period of aftercare, and after 30 years, we say, no chance. We have to prolong the aftercare time by around new 30 years. So we discuss them at the moment 60 years. But if you have, for example, MBT pre-treated waste, then the aftercare time is around smaller 30 years. This is a very important part, particularly for the question of operation cost. Last point for MBT, you remember that I show you how we can use the composting process for drying. And you remember we named it aerobic drying process. And you remember how it works? I will explain a little bit later. Again, the situation, we have some waste components like paper, cardboard, diapers, and an end. So if we have a low dry matter by 30%, that means a high water content by 70%, we have very low calorific values. But when we dry it up to 80% dry matter, vice versa means 20% of water, you can lift up the heating value from paper or from diapers by the double or factor 4. And this is the precondition for producing RDF, refused derived fuel. So we use a lot of drying systems. We have the conventional one, the convection dryer, the conduction dryer. You have drum dryers, you have conveyor belt dryers, but in this biological area, we use this aerobic dryer, so we can use the composting process. Or what is very interesting for Brazil, you can use solar dryers. So again, what is the process of aerobic drying? It's a little bit repetition. We blow in dry, cold air. The air will be heated up by the energy, the degradation energy. And you remember, degradation energy is heat. So you lift up the temperature of the air, and by changing the temperature, you lift up the holding capacity of air, the holding capacity of water in the air. For example, so
Now,
okay. Wunderbar, es war bei mir noch weg. With the air temperature of 30 degrees, so your input air, we have amount of water carry capacity, say it simply, of 30 grams. By 50 degrees, you have 82. And this is a simple drying process of aerobic drying, which you can do in every place of the world, not in the Antarctic, in the Arctic, but you can do it, for example, very good in Brazil and other countries. And the other component, for example, if we have the solar drying, these are greenhouses you use, greenhouses. The radiation of sun is moving through the glasses or through the plastic lines. And so the air inside these greenhouses will be heat up. And so you can dry your material by the sun inside this kind of greenhouses. Maybe inside these greenhouses, you have to move the material, you have to turn the material, because the drying effect is only on the surface. And for example, Christian and me, we have made a concept for the drying of sludges. It's a very simple technology. It is a more or less cheap technology, and it is very efficient because you don't need a lot of energy to take out the water. This solar drying is for me a very typical system which you can use, for example, in countries like Brazil or in all countries where you have long time enough of sun. And particularly, it's very well developed for different kind of sludges. We use it, for example, in Germany, in this shit cold weather in Germany. So the efficiency is okay, but it's much more better, for example, in areas like Brazil. The biggest one I know is on the Balearic Islands, on Mallorca. They have, I think it's a drying facility with around more than 200,000 tons of sludge. They dry it in this kind of solar dryers. So I think a special technology for countries for warm countries with a lot of sunshine. Lessons learned. You can, when you have these slides, you can read it and you can check your knowledge about what you have learned. And I hope I give you some ideas about this MPT technology. Background is that I know that there's a huge direction, for example, in development in Brazil to implement such kind of technologies. Last but not least, what can we do, for example, with this RDF, this refused derived fuel? You know that, for example, the cement production is looking for such kind of fuel. And I know you have some companies in Brazil, they have huge interest and they support different kind of measures in the area of waste management to produce this kind of material for producing fuel. Last point, there's a very strong development at the moment in Germany and in Europe to reduce the greenhouse gases from the cement production process. And this is also one of the big 6 in the world. What can they do? Around 50% of their carbon dioxide emission comes from the use of energy. They use coal, they use oil, and so now we have a pricing. The people have, when they use such kind of fuel, they have to pay a lot of money in the future for every carbon dioxide kilogram. So the development in producing fuels from waste with low fossil components means you have to dry your waste, you have to produce the fuel from your biomass, but taking out, for example, the plastic by sorting out before. And at the end, you have wood and you have, for example, the organic matter, the kitchen waste and the garden waste. When you have dried it, you can use it as the fossil-free fuel for the cement industry without paying penalties. And this is, for me, a very important development we have here, and I'm sure when you take out your special president all over the world, we will have this direction, trying to use fossil-free fuels to reduce the greenhouse gas emission. So, second lecture today, biotechnologies. We talk about exhaust air emission purification. And what you see on this picture, sorry, I need my pointer. I will talk mainly about biofilter technology, what you see here on the picture. So at first we have to talk about what kind of emissions we have, what emission categories we have. The main point in former times was odor emission, smelling. But meanwhile, greenhouse gases have the same importance. I think at the moment, the importance of greenhouse gases is much more relevant than odor emission. A special component is ammonia because it is a precursor of greenhouse gases, a precursor for methane or laughing gas. Also, we have some organic and inorganic harmful components and dust and germs. But we talk today only about odor and about greenhouse gases. So it is a terrible table, I know, but you have to work with it. You see on the left side the process areas. So the process areas, and on the right side you see the time of emissions. So delivering area, you have a lot of odor emission, you have a lot of germs. Preconditioning, the same. Now the most important one is the aerobic stage. That means the composting stage. At the beginning, you have greenhouse gases and you have odor and also germs. Anaerobic stage, normally it is a closed process, but when you take the material out, when you dewater it or when you bring it to the aerobic post-treatment, there you have a lot of greenhouse gases and odors. All other components are not so important. What is important when we talk about the concentration of odor? And then you see in this picture, you see here, we have a logarithm degradation, and you see that in the first 14 days, you have the highest amount of odor emission. Background is, in this first phase, you have very easily degradable organic components. So they degraded very fast, and they need a lot of oxygen. And in this time, you have the biggest problem to have enough, to have sufficient oxygen levels for the microorganism. And when you don't have enough, then you have the problem of anaerobic situation, of anaerobic condition. And anaerobic condition is the best circumstance and the best milieu for the creation of odor components. For example, some pictures how to take samples for smelling or for odor emission, or also greenhouse gas emission. You capture it on the top of the composting or of the biofilter, or you see here another kind of technology of sampling. It's not so easy to take out samples which bring reliable results. As a second step, so at first you take the samples in plastic bags, and then you use your nose. It's the so-called olfactometry. We have some people, normally you take students, and you have, for example, the sample giver. You take in here your sample, and you have a sample giver for every nose, and you start with an absolutely clean air. And then you add step by step your collected sample. In the first moment somebody of you recognized smell, then you gave a sign, and this is the concentration level of the raw gas is the opportunity to measure organic amounts and organic smell concentration. Second, greenhouse gas emission during composting and anaerobic digestion. So we look for methane and we look for laughing gas. Here we have composting and fermentation. Now you see composting only 1.3, fermentation 3.7. And when you consider, for example, the global warming potential, then we have 35 kilogram carbon dioxide equivalent per ton of bio-waste, or 93. At the same level we have with laughing gas. So the fermentation, the concentration and the amount is higher. Why? Main point of methane is the post-composting process of fermentation residues for the material after fermentation. So you have in your material you bring to the post-composting process anaerobic components, and you have anaerobic microorganisms. So, and they produce a lot of methane. So this is the background for the requirement. You have to stabilize these fermentation residues very intensive by using oxygen. And when you blow in enough of oxygen, then you stop this methane situation, this methane production, so you can reduce this amount of methane. So in Germany, we have at the moment the law, we must have an aerobic stabilization process. That means nothing else than blowing in a lot of oxygen. And you have to do it in a closed area. So you have to collect the air. The laughing gas, it's another point. Laughing gas we produced in the combination of composting and fermentation. Background is that we don't have enough of carbon components for the need nitrification and denitrification process, so that at the end we don't have enough of carbon. So at the end, the dead end of nitrogen is laughing gas. So this is the situation, but the most problematical way is these gases, methane and also laughing gas, move in a biofilter in a special concentration and moving out of the biofilter in the same concentration. So the efficiency of biofilters for this kind of greenhouse gases is more or less very low or is zero. We will talk a little bit later about it. So again, this problem, we have ammonia, this is the green, we have methane, this is the red line, and at the end we have the dark line is laughing gas. So when we have this post-composting process of residues from fermentation, you have first a lot of methane, but by oxidation, by blowing in oxidane, the amount of methane reduced very rapidly. On the other hand, you have an increasing of ammonia, and in the middle of the post-composting process, it starts cause of missing of the lack of carbon, the production of nitrogen, the production of laughing gas. This line we find very often in the area of post-composting of the residues from fermentation. So these are some preconditions. Now we enter the area. What can we do at first as measures for exhaust air purification? And we divide these measures in primary measures and in secondary measures. So secondary measures is, for example, construction of collecting the gas and the purification in different kind of filter technologies. But the main point is, how can we minimize, how can we mitigate the emission in the process so that we don't have any emission? So this depending, for example, in the raw material. If you have enough of structure materials so that that you have enough of air pore volume, so that you have enough of oxygen, so you don't have any kind of problems with anaerobic condition. You need a right humidity. So if the material is too wet, so you have a very high potential of anaerobic situation, and that means a lot of smell and a lot of methane. Another point, temperature. Why temperature? The problem is over 60 degrees. We have some special products which has a very high amount of smell, of odor. So try to reduce the temperature below 60 degrees. On one hand, the consequence, you have much more higher degradation rates, but also you have a reduction of the creating of odor components. So process technologies, sure. For example, turning technologies, aeration technologies, air management, protection against precipitation, and all these technologies are very important for the reduction of the amount and of concentration of the gas for odor and the greenhouse gases. And the second measures, I mentioned it, we will talk now. We talk mainly about exhaust air purification by biofilter technologies and also by ammonia scrubbers or acid scrubbers. These are the two main technology I will describe. But again, let me show two simple pictures. We have, this is we called it a triangle windrow or triangle pile, compost pile or compost windrow. What you can see here is the amount of oxygen concentration. You see outside we have percentage of 15%, maximum, remember, 20.8. But when you go inside your windrow, the amount of oxygen is much more lower than outside. In the outside area, you have a diffundation of oxygen, but here a diffundation is not possible. So inside this area, you have the biggest problem. This is the reason why we blow in oxygen, why we suck out the air out of the pile, and we integrate oxygen from the outside layer, from the surface into the pile. So we have two options: blowing in oxygen or sucking out air by taking in oxygen from the surface of the pile. And the second step is windrow turning every week or every 3 days or every 4 days, depending on the air management. So again, two options: active way of aeration. Second is taking the right turning systems in this turning frequency. And again, the third point, use a good raw material, not too wet and not with only a low amount of structures material, means don't take material with a low amount of air pore volume. So the mixture of the raw material is very, very important. And now the second point is the same pile. And here you see the amount of methane inside the same pile. And you see there's a very clear correlation between carbon dioxide and oxygen availability. We have in this area no oxygen, so we have in this area consequently high amount of methane. So again, to take out or to hinder the microorganism to change from aerobic to anaerobic processes, put in oxygen. So now we finalized the primary measures, and now we're looking for the filter technology. The biological filter technology is biofilter, bioscrubber, and we also will look for the washer, mainly the chemical washer, or it's called also acid washer. We start with more or less 10 requirements. We call it field house criteria. Forget this name, the criteria are important. This is criteria for the filter technology in general, if biofilter or chemical filter, independent from this. This is the requirement at first: effectiveness in limiting of emission. I don't think that I have to explain it. Sure, the filter technology must have a high cleaning performance. Plant safety. What does it mean? For example, explosion. We have a lot of problems, for example, with dust explosion. When you have dust filters, you have problems with fire protection and. So plant safety. When we talk about biofilters, we don't have to pay attention on plant safety. System availability. What does it mean? When you have a filter technology, it has more or less work 100% the year. Because when you have only 80%, then you have 20% of lot of emission. And the people will like you very much when you have a technology with a low availability. So when you have, for example, some technologies in the incineration, it could be that the filter technology will be failed because of siloxanes you have in the filter technology and they blocked the throughput of the air. When we have biofilters, for example, they dry out, they are not working. Or when you have a biofilter and you have to change the filter material all 3 years, what do you do? So you have to randomize. We have to talk a little bit later. So in general, the requirement is 90% of availability over 1 year. So maintenance, that means how much time you need for maintenance. 1 day, 2 days, 1 month, 3 months. Lifetime of the plant. Biofilter, it's set to maximum 5 years for the filter material. After it, you can't use it again. Consideration of startups and shutdowns is the same situation according to the availability, but you have to know when you want to bring in a biofilter in running, you need 3 to 4 weeks for the adaptation of microorganisms to the special exhaust air you bring in this filter system. Energy expenditure, it could be that some filter technologies use a lot of energy because you have to add energy for the burning process. But it's independent, nothing to do with the biofilter technology. Space requirement, I think when you use biofilter technology, in general, they have a very high space requirement, but there are some solutions I will show you later. The last 2 points, generation of new pollutants. What is this? We know, for example, from incineration plants that we have a so-called de novo synthesis. De novo synthesis of furanes and, for example, other components, furanes and dioxins. This means PDCC. Oh my God, I forgot the right name in English. Polychlorinated dibenzofurans and dibenzodioxins. But we have also in the RTO, this is a burning technology of the air from MBTs. Maybe the burning process can produce laughing gas. And we know it from biofilter. When you don't enhance the process on a right way, it could be that you produce laughing gas and the raw material, the precursor, is ammonia. So all these components you have to consider when you design the air purification technology. And again, to biofilters, we use it all over the industrial area for wastewater management, in the food industry, agriculture industry, slaughterhouses, but also in industrial production plants. For example, printing plants and paint shops and. So there are a lot of options for usage of biofilter technology. So, but at first, what are the principles of biofilter technology? Principle, activity of microorganisms that biochemically oxidize, sorry, 1E too much, organics, exhaust air, constituents, and adsorption. So the main point is that the filter material fixed for a short moment the organic components, that the microorganism can degrade them by the aerobic way, by using oxygen. This is the most important thing. So what kind of raw materials for the application of biofilter you can take? They must be water soluble and biodegradable. components which are not biodegradable, you can't filter in the biofilter technology. And the main other point is the temperature is in a very small windrow. So that means the optimum of degradation rate and filter efficiency is by a temperature between 35 and 38. And you have to pay attention, because if you take the air from a compost facility, it's possible that you have 60 degrees in the exhaust air. So the regulation of the air input in the filter according to the temperature is very important. It's a very important question. And it's also sure, because that you have a good throughput streaming through the filter material, it is very important that you don't have any dust and grease inside your air. These are, for example, the main aspects for the filter material, for the biofilter. And here you see some design of a filter technology. You see, at first we have the exhaust air from, for example, from a compost plant or from an MBT plant. You have an air van which transported in this air into the biofilter. At first, you have a dust separator, because the dust is blocked the air pore volume in the biofilter. Normally, you combine it with the humidifier, because you wash the air, you lift up the humidity, and in this case, you in the same step, you clean the air from the dust. And then you have the temperature regulation. Normally, you have some ventils so that you can bring in outside temperature. Very important is not too low temperature. The problem is too high temperature. Again, 35 to 38 degrees. So at the end, you bring this air in a so-called distribution chamber or mixing chamber, and from this chamber, the air moves through the biofilter, and you take out the purified air. This is the simple process of a biofilter. And again, in a biofilter, adsorption, fixing the organic components for the microorganism, then the microorganism has the time to degrade it by the composting process or by the aerobic process. A combination, again, of oxidation and sorption. And there are different kinds of filters. For example, if you have a huge problem with available space, you can have floor filters, very simple system. You can have windrow filters. For example, you can use the post-composting area as a filter system. You can use flat filters, you see here on the picture, and you can use container filters. Again, this is the background for if you have to reduce the amount of space. This is the normal filter technology you use in the area of composting. And if you have the requirement for extremely high efficiency in degradation rates or purification rates, then you take a biofilter, implement it in a container, because you can enhance the water content, you can much more better enhance the temperature end and end. So this is the same picture I showed before. And here's some pictures in reality. Typical biofilter technology with the inside air. You take it inside this area, and the air coming out of the filter is the purified air, and you don't smell it. I had a group with Brazilian people from, remember, Cristiano, you remember. We discussed 1 hour nearby a biofilter, and then I said, please, and now look, do you smell something? And they all said, no, we don't smell. And I said, this is the filter system it is running and you don't recognize a smell. So we hope that they were convinced about the efficiency of biofilters, but when I remember right, we don't convince them. Another point, for example, a problem for Brazil, for areas with high amount of sunshine. One of the biggest problems of biofilters is drying out the filter material, and without water, again, an aerobic degradation process can't take place. So you have to shadow it, or you have to bring in water inside the system. And again, when we talk about these requirements for the biofilters, the main requirements for the availability of 90% over a year, so you can randomize the filter. So you have 3 segments of filter systems. They are working independent from each other. And so when you have to change the raw material, then the other 2 filter beds are working. So 90% of availability is absolutely not a problem. Again, the same picture. Before we came to the dimensioning, we have to talk about structure, filter material. What kind of filter materials you can use for a biofilter? You need a good structure. That means you need a lot of air pore volume. It's at between 20 and 80%. So that the air can move through the filter material. Large surface of the area, large surface of the filter material itself, so that the microorganism, that the filter material can fix the organic components, that the microorganism can degrade them. No extremely pH value, for example, between 5 and 7. Very good is the high buffer capacity against pH value fluctuation. Then don't misunderstand when I say low rotting rates. It means the raw material, the filter material you can use, you will use it over 2, 3, 4, 5 years. So it's very important that this material is not easily degradable, because otherwise, after half a year, you don't have a filter material. You have a compost, and it's not working. So it must be very stable against composting processes. Low inherent odor, we don't have discussed this. The filter material is not allowed that the filter material smells itself. And we have to ensure that we have enough of nutrients, but normally the most filter material on the long-term view has a sufficient amount of nutrients. So you don't have to take care about this parameter. So some pictures again. So this is this floor and container filters. You see it in the praxis. You don't need a lot of space if you use such kind of filters. So again, these materials, you can use root wood. You can use wood chips. This is the main components you can use. But there are some other components, fibers, peat, coconut fibers, for example, interesting for Brazil. These are all materials you can use for a biofilter. And again, filter process parameter. Now, this is not the material we talk about now. Now we talk about the process parameter. At first, the most important part, the load. How much cubic meters I can enter the biofilter. And there we have a number. It's at 60 to 100 cubic meter exhaust air per cubic meter filter material and hour. This is a very simple dimensioning number, and I think in Europe we all use this dimensioning parameter in the area between 60 and 100 cubic meters. This could differ if you have special components in the air, but if you have a normal composting process, this is the parameter, the process parameter for dimensioning. The height of the layer is around 0.8 to 1.20 meter, maximum 2 meters. Length requirement, it's depending how you design the filter. So it is not so important what I give here. You can find all numbers. It's the question of how much filters you will, how much flaws you have on your filter technology. So operation temperature, we have talked about 30 to 38 degrees. pH range, we have talked about. Filter humidity, extremely important. When you don't have enough of water content, when the humidity is too low, microorganisms stop their degradation process and the filter material, the filter process came to an end. Mean resistance time in the air, 15 to 30 seconds. But you have this parameter and you have to combine it when you fulfill this requirement. 60 to 100 cubic meters per exhaust air per 1 cubic meter filter material in 1 hour. Then you have fulfilled also this main resistance time of the air. Filter resistance, I said to you, this is the pressure you have to realize, and therefore it's very, very important that the amount of porosity, for example, in this case, is up to 0.4 to 0.85. And in combination, you have also see the bulk density. So this parameter, bulk density and porosity, they are in one group to ensure that you have a free way for the migration of the exhaust air. So what could happen? Again, you have to protect the filter material against drying. You can irrigate it, you can shadow it, and so there are a lot of options. You have to pay attention of rats activity. For example, this is typical in Germany when it's cold. Rats are moving inside the filter material, and rats are loving compost and compost raw materials. That means in all facilities of waste management, we have a lot of rats. But when they going inside the filter, because it's so wonderful warm, so you have a so-called breakthrough of the exhaust air, and so the air is not moving through the filter material, it's only moving through these new holes created by rats. So at the end, we can have efficiency of more of 99% of biofilters according to odor. So at the end, a short dimensioning. You remember we have the volume loading in the volume exhaust air related to the volume of the filter, 60 to 100 cubic meters per cubic meter and hour. So here are some examples. You have a volume flow of exhaust air gas, of exhaust gas. It's around 12,000 cubic meters per hour. The filter height, in this case, 1.8 meter. And at the end, you have assumed volume of 80 cubic meters per hour. 80 cubic meters per cubic meter an hour. That means a filter volume of 150 meters cubic meters and have in consideration the filter high of 1.8, the result is an area of 83 square meters. So when we talk about biofilter systems and odor reduction, the system is working very well. But when you see here the results of methane, of laughing gas, then you see the efficiency of biofilter technology for methane and laughing gas. For methane is more or less plus minus 0, but it could be with nitrogen you have a production, laughing gas. It could be that you have a production. How to reduce the potential of new methane and new laughing gas? Background, the reason for the creating of for so-called de novo synthesis of laughing gas, the reason for it is ammonia. And maybe the creation of methane could be also ammonia. So ammonia we have in the biofilter in the biotechnologies like composting and fermentation, only in the fermentation process, because we have a high concentration of ammonia. And this is the reason that we required, meanwhile in Germany, you must integrate an acid scrubber before the biofilter technology. If you use an anaerobic process, that means if you use a fermentation process. When you take out the ammonia, this NH3, before the biofilter technology, then the problem of de novo synthesis and laughing gas you can reduce up to 0. And what does it mean? It's very simple. You take in this acid, and this acid, this sulfur acid, you have a reaction with ammonia, and at the end you take out this ammonia in a combination of sulfur and nitrogen. But with these components, it is not possible to produce, to come into a de novo synthesis caused by ammonia. So you have this ammonia sulfate. And this ammonia sulfate you can use at the end as a fertilizer. So all these products of the acid scrubber we use, for example, in Germany as a fertilizer for the agriculture use. Meanwhile, on all waste management fermentation facilities, we have this required combination of acid scrubber and biofilter. And in total, you see the combination of the system. At first, you have the system with acid scrubber and the purified gas free of ammonia entering in the biofilter technology. And so you don't have a problem of laughing gas and nitrogen. The last picture shows some efficiency numbers we had in a facility in Helsinki, in Finlandia. There I measured the highest emission of raw gas odor. We have numbers about 150,000 odor per cubic meter. This was extremely high, but this is not a problem when you have, for example, a biofilter and you have find the right dimensioning. So at the end, you can say, with the right dimensioning, with the right process enhancement, particularly according to water content and air pore volume, then an efficiency of around 99% according to odor is possible. Another point, biofilter technology is not a filter technology to degrade methane or laughing gas. So this was my last slide. So thank you very much for your listening.